Hello everyone, welcome to the third episode of me learning Rust. Today we'll go over the third chapter in the book and try to learn some basics of Rust. Let's just read the intro. This chapter covers concepts that appear in almost every programming language and how they work in Rust. Many programming languages have much in common at their core. None of the concepts presented in this chapter are unique to Rust, but we'll discuss them in the context of Rust and explain the conventions around using these concepts. Specifically, you'll learn about variables, basic types, functions, comments, and control flow. These foundations will be in every Rust program, and learning them early will give you a strong core to start from. Keywords. It says that there are keywords in Appendix A. We'll not go there right now, but what I'm expecting is some examples, some way of using variables, using if statements, maybe some of the match statement we saw earlier, and some other maybe control flow or type definition subjects. So let's just dive in. Okay, so variables and mutability. Wait a second, I don't see they ask us to start a project, so I think we'll just do cargo new chapter 3 and then go to chapter 3 and just open VS Code. And I think we'll not need this thing and just do it like this. Okay, great. So let's start with the variables. As mentioned in the storing values and variables section, by default variables are immutable. This is one of many nudges Rust gives you to write your code in a way that takes advantage of the safety and easy concurrency that Rust offers. However, you still have the option to make your variables mutable. Let's explore how and why Rust encourages you to favor immutability and why sometimes you might want to opt out. Well, that makes sense. Yes, and I really like it that you have to be very explicit about the things that you do, that by default everything is immutable, everything is closed down. You can't do anything wrong unless you explicitly say that, okay, I want this variable, I want this thing to be mutable. Okay, let's continue. When a variable is immutable, once a value is bound to that name, you can't change that value. To illustrate this, generate a new project, call variables in your project directory, and using cargo new variables. Oh, okay, it asks me, but we'll just stick to chapter 3. Then in your new variables directory, open the main rs file and replace the code with the following code. So let's just do it. I guess this will not compile because I'm trying to change x, but just making sure. I'm not going to even compile it. I'm just going to do this and wait for the squiggly lines. No squiggly lines. Oh, because it did C. Okay, now there are squiggly lines that says this is an immutable variable of x. Wait, why C didn't do anything wrong? Can I just define? Okay, this is something interesting. I do cargo run now. Okay, now it says it's wrong, but when I typed it, well, maybe it's just a difference between the cargo check and cargo build. Let's see if I do cargo check. Yeah, it still says so. And if I just delete this, save this, do a cargo check. Okay, this is unused. I'm expecting this. So if I do again, C equals 6. Okay, now it says it's an error. Okay, maybe it was just a hiccup with the compiler. Okay, great. So yeah, if I do something, it's by default immutable, and I just can't reassign it. It's just like a const, basically. Okay, this is the error. You received an error message, cannot assign twice to immutable variable x because you tried to assign a second value. Okay, great. It's important that we get compile time errors when we attempt to change a value that's designated as immutable, because this very situation can lead to bugs, of course. If one part of our code operates on the assumption that the value will never change and another part of our code changes that value, it's possible that the first part of the code won't do what was designed to do. Okay, yes, makes sense. But mutability can be very useful and can make code more convenient to write. Although variables are immutable by default, you can make them mutable by adding the mute in front of the variable name, as you did in chapter 2. Yeah, okay, that makes sense. The reason for variables to exist is in order to input some data into the flow of the program. Yeah, if we just had consts, it'll be very, very boring programs. So let's just try to do this example. Okay, without the let x equals 6. So now it says it's an error, but the second I put in mute, it should all be okay. Of course, let's just print x for it to stop the warning. Hello x. Okay, this should work. This is an unused value, probably. Yeah, I've written before it is read. So we'll just do this, and it should work. Let's just try to run this. See that everything is okay. We're building. Oof, took it 1.6 seconds to build. That's a very difficult, very intricate program. But hello 5, hello 6, everything looks okay. Okay, and yeah, this is the next example. Okay, now constants. Oh, there are constants. Okay, so I wonder what's the difference between the immutable variable and a constant. Like immutable variables, constants are values that are bound to a name and are not allowed to change. But there are a few differences between constants and variables. Okay, great. This is what I want to hear. First sentence. First, you aren't allowed to use mute with constants. Makes sense. Constants aren't just immutable by default, they're always immutable. You declare a constant using a const keyword instead of let, and the type of the value must be annotated. We'll cover types and type annotations in the next section. So don't worry about the details right now. Just know that you must always annotate the type. Okay, so with let, there's, I think, like, runtime or compile time typing, and with const, I have to type it in advance. Okay. Constant can be declared in any scope, including the global scope, which makes them useful for values that many parts of the code need to know about. I guess that means that I can't declare immutable variables in a global scope. The last difference is that constant may be set only to a constant expression, not the result of a value that would only be computed at runtime. Okay, so I assume like if I do something like this, let's just do const, my const let's say 5. Well, this should be an error because I didn't say what type is it. Yeah, missing type. So I already know how to use types. So now I define the type and it should stop being an error. Just a warning that I'm not using this constant. Let's also try to put this here, and it works. Great. And now let's try to do this, what they said that shouldn't work. If I'm doing this, I'm basically trying to initialize my constant with a mutable value. It says it can't. And also, if I'm doing this with an immutable variable, it shouldn't work. Okay, great. That tells me that these values might be like hard-coded or replaced into the code as an optimization. Yeah, they will not usually take up any variable memory. They'll just put the value where it needed. Okay. Yeah, I can do this. Yeah, so this should work. Should be okay. Let's see. Okay, wait, I'll do this. Great, this should work. I'm not using my const, but let's just print this out. So I won't have any error, any warnings. Let's compile and run. Okay, great. Now you know that 5 times 51 is 255. Great. The constant name is 3 hours and seconds, and the value set to the result of multiplying 60 by 60 by 3. Great. Rust naming convention for constants is to use all uppercase with underscores between words, and this is very common for consts. The compiler is able to evaluate a limited set of operations at compile time, which let us choose to write out this value in a way that's easier to understand and verify. Basically, what it says that this calculation is done at compile time, and I assume I'm not going to go into machine code here, but that eventually in the program, this gets just replaced by the number 255 in the code. Well, if I'm inspecting the code, maybe not in the debug compilation, but in the final compilation, I'm never going to see anything like this. I'm just going to see something like this inside. Great. Constants are valid for the entire time a program runs within the scope in which they are declared. Okay, this is interesting. This property makes constants useful for values in your application domain that multiple parts of the program might need to know about, such as maximum numbers of points and player of a game is allowed to earn, or the speed of light. Okay. So basically what it says that these live within the scope, and if I'm using a global scope, that it lives forever within the time frame of the program. But I think that the lifespan of this is the same. I think we should test it when we talk about functions to see like what's how the scopes work here. Like if maybe I'll try to do something like this. I define this within a scope, but I'm not sure that this is an inner scope yet. But just want to see if this is an error. Yeah, it's an error. So exactly, yeah. As I thought, the const is only valid within scope or maybe subscopes. It's easy to test that. If I'm just going to get this print function within the scope, should be okay. Great. Yeah. So now we know about scoping with constant values. Great. Shadowing, we looked at it with I think with a guessing game. There was the number guessed or something like that that we shadowed. So let's look at it. Let's declare x all over again. X equals 5, and then I'm doing x equals x plus 1. Then it's really okay. I'm not using it, so let's just print it. Oh, sorry. Print x. So it says I'm not using it. Great, let's use it. And now we're printing. It says it's mutable thing. Now I'm printing this x, it'll be 5 and then 6. So I'm expecting it to print 5 and then 6. Great. 5 and then 6. And here, what are they doing? Oh, this is interesting. I want to see how it behaves within a scope. So now x is 6. And now I'm defining a new x, which will be x plus, 4. I'm expecting it to be 10. If I'm doing it here, so what I'm expecting is to get print of 5, then a print of 10, and then, without reading, I'm expecting here to print a 6. Let's just run and see if, yeah, exactly. So this shadowing goes on within a scope. So this x still lives on. I'm just in this scope. I think even if I'm doing this, it'll be 5, 6, 10, 6. Let's just make sure of that. Yeah. So the second I define this x until the end of the scope, this is the x. Sorry, this x is shadowed by this x. And then when I go out of scope, I get this x back. Probably it works in the stack. Yeah, I just get a new variable, and the shadowing is in the compilation time. Yeah, okay, makes total sense to me. If you don't understand, you want me to write a little bit about this in the comments, you're welcome to do so. I just ask. Yeah, so this is, if we run this program, we're getting like this is 5, this is puts 6 into x, this multiplies by 2, so I'm expecting this to print out 12, and then when it goes back, it comes back to this value of x, which is 6, and this is exactly what we see here. Shadowing is different from marking a variable as immutable because we'll get a compile time error if we accidentally try to reassign to this variable without using the let keyword. By using let, we can perform a few transformations on a value but have the variable be immutable after those transformations have been completed. This is an interesting take. Yeah, that means I can still change this variable, keep it immutable, which is a little bit contrast to each other, but it makes sense when I think once we'll start talking about functions and passing functions as mutable, like passing two functions with mutable variables or immutable, and then I could control the value that I'm getting in the main scope. Basically, if I'm putting a mutable variable inside a function by reference, then the function can change it. It's no longer a pure function. But when it's an immutable variable, even a reference, I can be sure that even if someone uses the same variable name inside the function and changes this variable, when I go back from the function, when I return to the main scope, I'm still going to have the old value of the immutable variable. It's a little confusing right now, I think, but once we get into functions, I'm going to test all these things to see that they really work. But I think it helps with arranging the code and maybe saves time on renaming some variables just to get different types or different iterations of the same concept within a function or within some sub-functions. Okay, the other difference between mute and shadowing is that because we're effectively creating a new variable, when we use the let keyword again, we can change the type of the value but reuse the same name. For example, say our program asks a user to show how many spaces they want between some text by inputting a space character, and then we want to store that input as a number. Okay, yeah, this is a really good example that also allows us to do some sort of parsing of a variable, and then without assigning it to a different named variable, we just replace or shadow the variable that we used to get the information with the formatted information or parsed information instead. That's just, I think it's very convenient when looking at the program. You can just look at the name of the variable to know what's in there, but the type will change along the way. And I think with these hints, it will be easy to keep track of the type. I'm like not 100% sure, but we'll see. We'll see once we get longer programs. I'll try to use shadowing and just see how it feels to do this. I mean, you don't have to use shadowing if you don't want to, but I think it'll be good. I think it'll be easier to understand long programs when you have the shadows, especially with the IDE hints that I'm getting here. Yeah, I can, if I hover here, sorry, I need to be in focus. No, I'm not having this, but if I hover here, I can see it's in I32. And let's just try to change the value to a string, maybe. Yeah, so now it's a string. And if I'm looking at x here, and x here, sorry, and x here, should be able, sorry for the L, should be able to see that this is an I32 and this is a string. Okay, so if I'm getting this hints, I will be able to know where I'm going. Great, let's continue. Yeah, the first spaces variable is a string type and the second spaces variable is a number type. Shadowing thus spares us from having to come up with a different name, such as spaces str and spaces num. Instead, we can reuse a simpler spaces name. However, if we want to use mute for this, as shown here, we'll get a compile error. Okay, yeah, if If it's a mutable variable, you cannot change the type. Basically, the type is set in stone. I think looking at shadowing is something like creating a new variable. I think it will also have maybe a new location in the stack. Maybe not here. I'm not sure. Maybe it'll be some sort of like, I don't know, some shuffling, but it'll act as a new variable starting from the line here. And if we go to a new scope, then the old scope will keep the old variable. Yeah, I hope I'm making sense here, because I'm also trying to grasp this concept. And we're done with chapter 3. Okay, this is a very short chapter. I think we should go to chapter 4 as well, and still continue in this chapter 3 thing, talk about data types. Every value in Rust is of a certain data type, which tells Rust what kind of data is being specified, so it knows how to work with the data. We'll look at two data types, subsets, scalar and compound. Okay, keep in mind that Rust is a statically typed language, which means that it must know the types of all variables at compile time. The compiler can usually infer what type we want to use based on the value and how we use it, in cases when many types are possible, such as when we convert a string into a numeric type using parse, as we saw earlier in chapter 2. We must also add a type. Okay, makes sense. If we don't add the U32 type annotation shown in the preceding code, Rust will display the following error, which means the compiler needs more information from us to know which type we want to use. Okay, scalar types. A scalar type represents a single value. Rust has 4 primary scalar types: integers, floating point numbers, booleans, and characters. You might recognize these from other programming languages. Let's jump to how they work. Okay, integer types. I think I'm not going to read this. Just looking at the table gives me all the data. So we have 8, 16, 32, 64, and 128-bit integers. We have signed integers and unsigned integers. We also have an arch. Let's see that it's actually a thing. Yep. Which means that this is the size of the architecture, the default int, probably in the let's see what's written about arch here. Okay. Additionally, the isize and usize types depend on the architecture of the computer your program is running, which is denoted in a table as arch. 64 bits if you're in a 64-bit machine architecture, and 32 bits if you're in a 32-bit architecture. I think this will be mostly used for sizes, for offsets, for pointer types, if there are pointers in Rust. I'm not sure. But yeah, this is basically the hook that we have into knowing what the operating system can do with numbers and even maybe memory. Okay, you can write integer literals in any form shown in table 3.2. Note that the number literals that can be multiple numeric types allow a type's suffix, such as 57U8, to designate the type. Number literals can also use underscore as a visual separator to make number easier to read, such as 1000. Okay, this is cool. Let's just try this. So if I'm doing 1 million, this will be 1 million. Okay, if I'm hovering, it doesn't tell me the value. Let's just try to do y equals, I don't know, will this work? Yeah, I don't need this. I32, but there's no hint about the value. Yeah, when I code in C, if I hover above a literal, it also displays me the value. Like if I'm tapping in hex, it displays the octal value. The decimal value. Let's see if there's octal. Is octal an 8? That's an example here. U8. But that means this is U8. This is, that denotes the type. Okay. Great. That's better than C. Yeah, I can say the type. If I want to use this U182, this will change to U182. That's great. Okay, so can I do this? B. Lesbian number. Okay, great. So binaries and hex. Octal is with a no. Yeah, the underscore with binaries is really good. Can do this. Multiple bytes. I don't know, let's do this. But I still can't see the value. Let's just print. Let's just see what it prints, if it prints the decimal value or not. And it's interesting. We have X and we have the Y number. Let's run the program. There's a warning. Unused import core arch. Oh, didn't see that. I don't know why it did it, but okay, great. So now we have 1,193,000, which is this binary number. So we can do decimal numbers, we can do hex, we can do octal, binary, and a byte. Okay, byte. Let's check. Like if I'm doing just this, is this a byte? It's a char. If I do B, it's a U8. Interesting. What if I'm doing a U8 here? Oh, it doesn't like it. So only numbers can be done with this type annotation. And if I'm using just one character, it's of type character. And if I'm doing this, then it's of type U8. I wonder if there is any wording, any text about this. So how do you know which type of integer to use? If you're unsure, Rust defaults a generally good place to start. Integer type defaults to I32. The primary situation in which you use isize or usize is when indexing some sort of collection. Integer overflow. Let's say you have a variable type U8 that you can hold values between 0 and 255. If you try to change the value to a value outside of the range, integer overflow will occur, which can result in one of two behaviors. When you're compiling in debug mode, Rust includes checks for integer overflow that cause your program to panic at runtime. If this behavior occurs, this is very good. Rust uses the term panicking when a program exits with an error. Yeah, we saw that before in the previous chapter. We'll discuss panic in more depth in the unrecoverable errors panic section in chapter 9. When you're compiling in release mode with the - release flag, Rust does not include checks for integer overflow that cause panics. Instead, if overflow occurs, Rust performs two complementing wrapping. So basically, yeah, if I'm adding 1 to 255, I'm getting a 0. Great. Okay. Yeah, that's exactly what it says here. The program won't panic, but the variable will have a value that probably isn't what you're expecting it to have. Relying on integer overflows, a wrapping behavior is considered an error. Not always. Sometimes you just want to see that and get a flag from the compiler. Maybe in the Rust context it's frowned upon, but we'll see. They explicitly handle the possibility of overflow. You can use these families of methods provided by the standard library for primitive numeric types. Wrap in all modes with the wrapping methods such as wrapping add. Return the non-value if there is overflow. Okay, I'm not understand. So wrapping add, we have 250 U8, and I want to add 30 U8, and then I want to print line my Y. Let's delete this, and I have an error here. Returns. Why is it yelling at me? use of unstable library features. Okay, let's see more detailed error maybe. Okay. Use of unstable library feature core intrinsics. Intrinsics are unlikely to ever be stabilized. Instead, they should be used through stabilized interfaces in the rest of the standard library. Don't know what I'm doing wrong here. For more operation, try explain. Wait, if I'm removing this, what am I getting? Cannot find function. So if I'm going to quick fix, I can import this, and I have the error. Okay. Wrapping add, and there's checked methods. Okay, well, maybe there's some flag. Requires an unsafe block. Okay, we're not going, we don't know what's unsafe yet. I guess it's something like unsafe in C#, but I guess you can only use this in an unsafe scope. Let's just leave it for now. Let's see, let's just read and try to deduce from the tutorial what it does. This just does the wrapping, as I saw in the tooltip here in the hint. It just does the operation modded by the maximum value or the minimum value of this variable type. If we do a checked add or a checked multiply or checked anything else, we get a none if we have an overflow. And I think we get here a value and a boolean that says if there was an overflow or no. Saturating means it will just clamp the value and not overflow it at all, returning not returning an error probably. Okay. We still don't have an answer about the character types. I hope there will be some. Yeah, it's supposed to be close to the end of this chapter, where they probably talk about characters. Okay, so let's go to floating points. Rust also has two primitive types for floating point numbers, which are numbers with decimal points. Rust's floating point types are F32 and F64, 32 and 64 bits, respectively. Default type is F64. Because of modern CPUs, it's roughly the same speed as F32. That's right, but it's capable of more precision. I guess just Rust assumes that most computers now are 32 bits. Okay, this is how you define them. Yeah, let's just make sure. 1.3. I'm getting this as F64, and if I'm saying it's F32, then it'll be an F32. But let's try something else. If I'm telling us just see syntax that it's a float, and no, it doesn't like it. Let's try this, F32. Okay, that also works. So I don't have to define the type. I cannot implicitly say in the intrinsic value what's the type of float here also. And I guess this is redundant, but it should also work. Great. Okay, so let's see, that goes back to F64. Okay. Numeric operations. Rust supports the basic mathematical operations you'd expect for all the numbers and types: addition, subtraction, multiplication, division, and remainder. Integer division truncates towards 0 to the nearest integer. The following code shows how you'd use each numeric operation in a let statement. So I'm not going to type this, just going to see. You have addition is basic, division, multiplication, quotient. I'm dividing this. I think that'll give me the F64 precision answer. And if I'm doing this, yeah, the results should be -1 because it truncates towards 0. And this is -1.6667 or something like this. And it truncates to -1. And this is a remainder, very standard C style arithmetics. Each expression in the statement uses a mathematical operator and evaluates a single value, which is then bound to a variable. Appendix B contains a list of all operators that Rust provides. Okay, Boolean type. Let's just write this equals true, and it's a bool, true, false. The main way to use Boolean values is through conditionals, such as an if expression. We'll cover how if expression work in Rust in the control flow section. Okay, the only thing that I don't know about the Boolean value is what's its size on a stack. Is it like a 32-bit variable, or is it like a single bit, or I don't know, even could be 4-byte value. Byte or a 4-byte value. Missing this in the documentation. We'll maybe look into it in the future and see what the value is, just because I want to know if to prefer like a Boolean array for some flags, or just using unsigned integer for and ticking up bits for this. Okay, the character type. Great. Rust character type is the language's most primitive alphabetic type. Here are some examples of declaring char values. Let's see. I have C equals Z. That's what we tried to do before, right? So it defaults to char, and also if I define it explicitly, and let's just copy this cat and see here. This is also a character. I think it says somewhere it's a UTF-8 character and not a byte, not a single byte, but there'll be some chapter that talks about strings, and we could learn about this afterwards, or I think it's the next paragraph. Wait a second. Note that we specify char literals with a single quote, as opposed to string literals, which use double quotes. Rust's char type is 4 bytes in size, okay, great, and represents a Unicode scalar value, which means it can represent a lot more than just ASCII. Accident letters, Chinese, Japanese, and Korean characters, emoji, and 0 with spaces are all valid in char values in Rust. Unicode scalar values range from U0 to UD7FF, and UE this is, I'm not going to read this out loud, inclusive. However, a character isn't really a concept in Unicode, so your human intuition of what a character is may not match up to what a character is in Rust. We discussed this topic in detail in sorting UTF-8 encoded text with strings. Yeah, basically with all the UTF encoding, you sometimes have like trailing characters that eventually become one character on screen, in screen space wise, with the emojis or Japanese and Chinese text. Usually you write several Unicode letters that are combined together in order to do the glyph on a screen. Okay, and this will be in chapter 8, much later. Okay, compound types. Okay, I think we're done with scalar types, and now we go to compound types. Compound types can group multiple values into one type. Rust has 2 primitive compound types, tuples and arrays. The tuple type. Tuple is a general way of grouping together a number of values with a variety of types into one compound type. Tuples have a fixed length once declared. They cannot grow or shrink in size. We create a tuple by writing a comma-separated list of values inside parentheses. Each position in the tuple has a type, and the type of the different value in the tuple don't have to be the same type. Okay, I think this is similar to Python tuples. We added optional type annotations in this example. So actually, okay, when I declare the tuple, yeah, let's do this. If I do 500, 6.4 and 1 as the example, let's see if this code will do something automatic, and it will not. So I guess I have to declare this. Oh, wait, equals, sorry. Yeah, it's automatically defaults here. And if I'm doing this, it will change this. But I can also declare what types I'm having. Let's say everything is U32, F32, and then U32. This should not work because of the U64 here. But if I do this, everything looks cool. Let's try doing this. Yeah, it doesn't like it. Great, so basically I can define tuples. I hope it's not something that replaces structs. I really do. But it's useful. It's useful when doing return types with multiple values that you want to do. Unless you're using the enums, which we saw in previous chapters, you can just put a value into an enum, like a different value than a numerical one. So we'll see. We need to see when it's better to use tuples, when it's better to use the other solutions, like enums, and if there are structs, and see what's the difference, what the trade-offs that we have in the code and the runtime. Okay, the variable tup binds to the entire tuple because a tuple is considered a single compound element. To get the individual values out of a tuple, we can use the pattern matching to destructure a tuple like this. Okay, very similar to Python. Let's just call this a tup. And then I'm going to do let x, y, and z equals tup. And let's see that it deduces the values automatically. Great. So it's u, f, u. Great. Okay. So this is the example. The program first creates a tuple and binds it to the variable tup. It then uses a pattern with let to take tup and turn it into 3 separate variables x, y, and z. This is called destructuring because it breaks the single tuple into 3 parts. Finally, the program prints the value y, which is 6.4 in this example, not in our example. Oh, actually, also in our example, if I'm doing this, then it'll print the value y. And then I only have 2 warnings here. Okay, great. We can also access a tuple element directly by using the period followed by the index of the value we want to access. For example, will this work? No, but this should work, right? This should work, as we saw, I think, in the first chapter. Yeah. Let's just delete this to get rid of the warnings, and this should print 1. Yep. So it's like 0 indexed. This is really cool, but let's see if there's some hints. Yeah, I see here a hint, but it's not named like a structure. So basically, I have to guess what's in slot number 3 in this tuple or no in advance. I don't know how it helps us. Maybe just by making code more, lean. Well, we'll see. Maybe there's some explanation. This program creates a tuple x and then accesses each element of the tuple using their respective indices. As with most programming languages, the first index is 0. The tuple without any values has a special name, unit. This value and its corresponding type are both written like this and represent an empty value or an empty return type. Expressions explicitly return the unit value if they don't return any other value. Okay, so this is like a a null or a void. This, like if I'm doing this, let's try to print it. Let's see if I'm printing this. An error. Okay, so they're saying that the unit does not implement the format display. Okay, and what if happens if I'm trying to do this? Let's just let x equals this. Okay, this is just I don't know. I really don't know. Maybe we'll find out later how it's used in code, and like except of null. Is there any reason? No, void. Sorry, instead of void. Is there any other reason to use this? Okay, this was the tuple type. Now the array type. I think we'll go over the tuple type later when we have some more examples, and then maybe we deep dive more into the all the meaning behind the tuples and how they work in conjunction with the other parts of the language. Okay, the array type. Another way to handle a collection of multiple values is an array. Unlike a tuple, every element of an array must have the same type. Unlike arrays, in some other languages, arrays in Rust have a fixed length. Very important. We write the values in an array as a comma-separated list inside square brackets. Let's just do this. 1, 2, 23, 4, 5. Let's say how the type is denoted. Okay, so I already see that we, in order to define type for the array, we do the square brackets and then the type and semicolon the length. Let's just make sure. Okay, let's see what happens if I'm doing this. U32, 5. Will this work? It doesn't work. Okay, I guess it's not how you declare an array. Sorry, it's supposed to be a semicolon. Maybe it is how you declare an array. Okay, great. This is how you declare an array. Let's just try to print it also and see if we have an error or not. Array A. Let's just run this. No, there's an error because, again, you can't print an array. Let's try this type of accessor. Let's see if it works. Still no. Let's try it outside. Sorry. You can't access an array like this because it's a tuple. So I guess we can do it like this. Let's see that this works. Yeah, I get an array 4. And let's see if it works inside here. Guess not. Yeah, it doesn't work. So I have to keep it outside in order to print it. Okay, let's continue on. Arrays are useful when you want to your data to when you want your data allocated on the stack rather than the heap. We will discuss the stack and a heap more in chapter 4. Or when you want to ensure you always have a fixed number of elements. An array isn't as flexible as the vector type, though. A vector is a similar collection that the collection type provided by the standard library that is allowed to grow and shrink in size. Okay. If you're unsure whether to use an array or a vector, chances are you should use a vector. Chapter 8 discusses vectors in more detail. However, arrays are more useful when you know the number of elements will not need to change. For example, if you're using the names of the month in a program, you would probably use an array rather than a vector because you know it will always contain 12 elements. So what I'm getting from this is that arrays are fixed length and I cannot change the length of an array. And if I want to use something to iterate over something that's unknown size or something that the size changes, I should use a vector, which we'll get to later. And I should only use arrays if I have a fixed number of values, at least at compile time. Yeah, I think it's okay to change it while I'm programming. If I want to add maybe a 13th month or something like that. Okay, this is how I write this. This is how I define the array. Let's just check something. If this does not agree, yeah, it's an error. Okay, so basically what happened here that I said the array is of length 5 and I provided an intrinsic of level 6, of length 6. And if I get this back to level to 5, then it's good again. Let's just make it compile. So everything will be cool. Okay, great. Let's continue. Here, I32, yeah, is the type, and 5 is the number of elements. I can also initialize an array to contain the same value for each element by specifying the initial value followed by a semicolon and then the length of the array. Ooh, that's interesting. I'm doing this and this. Should work. Semicolon. Sorry, not a colon. Okay, great. So this works. That means that I have an array with only ones inside. Great. Okay, accessing array elements. That's what we saw. It's very C-style-like, not with a dot, like the tuples. Also starts with 0. The first element is indexed 0. Invalid array element access. Okay, this is the overflows. Okay, let's see what happens if you try to access an element of an array that is past the end of the array. Say you run this code similar to the guessing game. Let's see, we have an array A, and we're looking for the access. Okay, so I'm just typing in the number, and if I type a number that is greater, I'm getting a panic. Index out of bounds. Okay, let's see if there are anything about doing this in release mode or debug mode. Okay, let's read through this. I think this is important enough to read everything. Okay, let's see what happens if you try to access an element of an array that is past the end of an array. Say you run this code similar to the guessing game in chapter 2 to get an array index from the user. The code compiles successfully. If you run this code using cargo run and enter 1, 2, 3, or 4, the program will print the corresponding value at the index in the array. If you instead enter a number past the end of the array, such as 10, you'll see this output. The program resulted in a runtime error at the point of using an invalid value in the indexing operation. The program exited with an error message and didn't execute the final print line statement. When you attempt to access an element using indexing, Rust will check that the index you're specifying is less than the array length. If the index is greater than or equal to the length, Rust will panic. These checks also happen in runtime, especially in this case, because the compiler can't possibly know what value the user will enter when they run the code later. This is an example of Rust's memory safety principles in action. In many low-level languages, this kind of checks is not done, many languages. And when you provide an incorrect index, invalid memory can be accessed. Rust protects you against this kind of error by immediately exiting instead of allowing the memory access and continuing. Chapter 9 discusses more of Rust's error handling and how you can write readable, safe code that neither panics nor allows invalid memory access. So I guess it also happens in release mode. There's an overhead, of course, because every time I access an array, I have to perform a check, and if I have some loop of massive amount of data that does this check, then it will have some performance cost. So I'll have to remember that when I'm doing indexing to maybe circumvent this somehow. Well, maybe chapter 9 will have some solution if I want to just go over an entire array, and I don't want the overhead of doing this out of bounds check. This is the end of the episode of of the chapter. Let's see what's next. Next is function. I think this is a very good spot to stop here. We talked about a lot, basically talked about types, about tuples, about arrays, about mutability of variables, about constant values. That's it. Thank you very much.